Hey guys, welcome back to Genius Learning. All right, I want to take a look at an E&M problem. And so we have a cylinder, right? And this is a top view. So we have coaxial cable consists of a copper wire, right? And the whole thing is the copper wire surrounded by concentric copper tube radius C. So this entire thing, and this is the wire in here. All right, the space between B and C here is filled with a material of dielectric constant ER. Okay, and it's asking us to find the capacitance per unit length of this cable. All right, what the hell does that mean? Well, first, let's break this down here. The capacitance per unit length. All right, so they're asking me to find something with the units of capacitance per, so it's divided by length, a unit of length. So I know that at the end, this is what I want. This is what I want to find. Now, how to get there is going to be a couple different things throughout the process. So let's start off with, let's see, get a color here. Okay, let's start off with using Gauss's law for electric displacement. So let's write the formulas here in pink. So we're going to be using, so first let's start using, so this is separate. This is like what we need to find at the end, right? This is what they're asking us. Here I'm going to start something separate. So using Gauss's law for electric displacement, right? Anytime we're inside dielectrics, we kind of always want to start here, or electric field. So this is what I'm going to start off with, is equal to the charge free enclosed. Okay, you should be familiar with this. So now this is going to be the flux associated with the electric displacement vector, right? How the electric field is flowing through the different materials. So let's set up this left side. So the left side is going to be two integrals, right? And since now we are in a cylinder, right, we're going to do 0 to 2 pi and 0 to L. So let me just show you here quick. A cylinder. Okay, this is up in the Z. Y is here. This is X. So we have phi coming like this, right? R is outward like that, and Z is up right here. So it's gonna be R, Z, phi. What we're looking at, and what we want for the surface, okay, what we want as a surface is going to be, let's see if I put in another color here. I'm going to do, okay, we want a distance out of R, right, like this, and then I want to sweep across a distance of d phi, right, because this distance here is phi, and then if I move a little more, this distance is d phi. So I want r d phi, right? So what I'm gonna do here is I'm gonna leave the d as is, right? So I want r d phi. So that's gonna be this arc length here, right? And then I want a certain distance, a certain length, right? The length of this, the whole cable is length L. And so in the Z, right, we want a certain length of these two arcs. So if you're a little confused about this, I have another video showing how to derive exactly these coordinates and these the double and triple integrals. So take a look at that if you're a little confused. But the next thing we're going to be integrating is dz, because we want to know the height. Okay, so that's it for the left side. And then on the right side, we're just going to put q, all right, a general q charge, and that'll represent the charge that's free enclosed in this system. Okay, and so here we're going to get d, this is vector, we got 2 pi from that integral. We keep the r, and we integrate, bring down L, and we got q on this side, finally we got Q over 2 pi RL in the radial direction. So the radial direction is outward like that. Okay, so like this, like that. Okay, so let's see. Maybe I should have put the radiuses here. So this distance here is A. This one all the way out to the edge is C. And let's see where we can put B. B will be on this side. B goes to the blue part. All right, so those are the radiuses. Okay, so this is what we have for electric displacement. Okay, electric displacement. All right, now the next thing that I find easy to find once I find the electric displacement is electric field, because we'll be using electric displacement is equal to epsilon, absolute epsilon, and times the electric field. So we're going to be using this equation. All right, rearrange it so we can have electric field equals electric displacement over epsilon. Okay, and this is for electric field. So before we do that, let's define something real quick, and that's going to be this absolute epsilon. So absolute epsilon is going to be equal to epsilon naught times epsilon r, which is the dielectric constant inside, and this is the for free air, like space, so vacuum. When you're in a vacuum, we use this, and here's for a specific dielectric constant. Okay, so we're gonna keep this in mind, and we're gonna rearrange it also to be ER is equal to epsilon over epsilon naught. One of the books has epsilons written this way. If I mess up, then you know, you can also write epsilon like that. So instead of like epsilon naught, sometimes if I write like that, these both mean the same thing, just in case. All right, so we keep this in mind. Now let's get the electric field for the different regions. All right, so let's start off with, let's see if I can squeeze it here. I'm gonna write it smaller so I can squeeze it there. So we got electric field, right? And let's do 3 different regions, right? So first we're gonna do the region where R is less than A. So R less than A is like in here, right? So what is the electric field in there? Well, inside the pink area, right? You're inside of the conductor. So you're not, this is the conducting material, all right here, and then inside the pink is nothing. And so electric field in the vacuum is 0. Okay, and between A and B, so now we are here, somewhere there. So R is somewhere here between A and B. Now we're in the conducting material. So let's take what we have for the dielectric electric displacement, which is this, right? And we're gonna put epsilon naught underneath, but we need to identify which epsilon we're gonna put. So we're gonna put Q over 2 pi RL, and we're gonna have epsilon naught in this region. Okay, that's for the conductor. And then now for the outside, or not the outside, for the area where you're between B and C, then you're gonna have specifically the dielectric constant that was given. So let's write ER. Actually, we're gonna just write E. Okay, so this one is epsilon naught, and this one is absolute epsilon, and we're gonna leave it like that. Okay, So this, let me box it up with this. This is the electric field in the 3 different regions. Okay, so I move it up. All right, so we're leaving it like that. So it's going to be a general case. Right now, we're going to change it up when we look at polarization. So in case you're wondering or you're kind of questioning this part, this next part might clear it up a little bit. So give me a second. Let's move on to polarization. Okay, so let's go over here. Now, let's do polarization, because polarization has the E variable, electric field, and so it's usually another good place to continue. So using, and let me label this electric field. Okay. All right. Using polarization equal to epsilon naught chi E and electric field. Chi E is the susceptibility, and so what that means, or basically what chi, epsilon, and k, which we don't have in this problem, they all represent is how the electric field acts inside of the conductor, inside of a dielectric constant, in between both. And so they all represent how the electric field behaves inside of those materials, all right? So we have this equation now, all right? Let's expand our representation for epsilon. Okay, we have epsilon equal to epsilon naught 1 plus chi E in parentheses. Okay, we can also write the absolute epsilon like this. Remember that chi E is 0. So chi E is 0 in a vacuum. Okay. So if chi E is in a vacuum, or it's outside of the conductor dielectric material, then it's 0. And then E, the absolute epsilon, is just epsilon naught. Which makes sense, because every time you're outside in free space, we put epsilon naught, not thinking that chi was equal to 0. That's the reason why we're left with epsilon naught. Okay, so keep in mind that this is the full equation. And let's write, okay, so ER, epsilon R is equal to 1 plus chi E, which is this part. So really, we have epsilon, let's see, we have ER, all right, minus 1 is equal to chi. Let's solve for this chi from this problem. So we'll leave these two together. But yes, this ER is equal to this, meaning this epsilon is equal to epsilon naught, epsilon R, just like we have here. Okay, so nothing changed, except for now we expanded the representation here of ER. Okay, so we have these things. Now let's try to get values for polarization. All right, we got polarization in 3 different regions, just like we have electric field in 3 different regions. The electric displacement is just general, and so it's the flux, right? Electric displacement vector through each of these materials. So that's why this one is generalized. This one has very specific values in each region, and so does polarization. So polarization, right, we'll call it 1, and that'll be for the region R less than A is 0, because electric field is 0, and so polarization is 0 in that area. All right, polarization 2, we'll say that that is all the way outside. We'll say that here, outside here is 2. Inside here is 1. All right. We're skipping the middle part because I want to show the middle part last. So the polarization all the way outside, we have, remember that in a vacuum, or like outside of a dielectric material, chi E is equal to 0. And so this is equal to 0, meaning polarization in that region is equal to 0. And this is for, let's put chi E in a vacuum. Okay. Okay, and that is for outside. So R is greater than C. All right, and now the region that is interesting, polarization for region 3, which is inside of here. All right, we have epsilon naught. Okay, so let's write epsilon naught, and then we have chi, right? Which, let's see if we use a different color. Okay. So we have epsilon naught. We write epsilon naught here. We have chi E, and we solved here for chi E. Okay. It all of a sudden appears because now we're inside of a material. So if we're in a space where there's nothing, there's air, there's no conductors, nothing is 0. Outside in the vacuum area, the same thing is 0. Inside here is where it gets interesting, and we have to introduce chi again. That explains more specifically what happens to the electric field in these materials. So chi E is ER minus 1. All right, and then electric field in that region, which is outside. So we have this, I'm sorry, not outside, in between here, right? So we have here, let's see, this one right here, B and C. Okay, so let's write Q over, okay, 2 pi R. So electric field is electric displacement, so it's this, so 2 pi L over epsilon, and the epsilon that we're in is represented by absolute epsilon, right? See how we left it plain? Now let's represent it with the specific epsilon that it is, because this is absolute, this is detailed for the material you're in. So I'm gonna write, instead of just epsilon, I'm gonna write epsilon naught, and I'm gonna write 1 plus chi E, right? So you see why I left it general over here, because now that I'm within one of these regions or outside or whatever, this needs to be explained in detail with this representation. Okay, so we have this, and this is a vector, so in the radial direction, right? Because the dielectric displacement is just moving outward. All right, so we got epsilon naught can cancel out, and what else? Okay, this might look a little tricky, but this 1 plus chi E, right, is epsilon R. So here is epsilon R, and I'm gonna distribute this epsilon R, which is now this whole thing, into here. So let me just write that part out again. I'm gonna put P3. Okay, I'm gonna do this epsilon R minus 1, right? This whole thing is epsilon R. I'm gonna move it outside and put it underneath here. Epsilon R, okay? And then what I have left here is Q, the same thing. So 2 pi RL R hat. All right, and then I guess to clean it up a little better, we got the polarization in that region is gonna be equal to, this is 1, and minus, this is E epsilon R to the negative 1, Q over 2 pi RL in the radial direction. So this is the polarization, right, in region 3, which region 3 is between B and C. So right here. Okay. And over here is the region to B. And here is C, just to make it clear. All right, so then we got these two also that were 0. Okay, so that's it for polarization. Now, let's take a look at the net potential. All right, so, might be running out of space. All right, so let's do this. We got, let me see if I have enough space here. I probably don't. Let me get another paper here. 1 second. Sorry about that. Just don't want to write small. All right, so let's see. What do we need from here? We'll need the electric field, so I'll move these in and out when we need them, and maybe I'll leave this down here like that. Okay. All right. So now for the next region. All right, we want, let's see, we want the net potential. So let me see what I got. Okay, so using phi, which is potential, right? We could also write V, negative C to A, electric field dotted with dr. Okay, and I think this is, okay, so this is dl, a differential length, right, vector. And then we know it's in the dr. So I'll write differential length just to keep it with vector notation. Okay, and then let's solve for that. So we need to find the potential, right, for all the regions. We want the net electric potential. And so the potential, if you remember, is from the outside in. So here, this cylinder, okay, I think it has another layer in here, something like that. Okay, we want to go from the outside. We're starting from some infinity and working our way in, okay, to this first layer, which is C, second layer, which is B, and in the original drawing, there's 2 layers out here. So let's say there's one in here, and that's A. We don't want to do the outside area here. So let's see. We don't want this area here. Okay, we only want the net potential inside the dielectric. What's happening inside of the material? Okay, that's why we're not interested in that outside part. And so knowing that, we're gonna do negative C to B, right, which is C to B, this first one right here, and the electric field in that region, dotted with dr, minus the integral from B to A, right, B to A, so, and then we got the electric field in that region, dotted with dr, minus A to 0, so all the way to the center. And electric field in that region is 0, so I'm just gonna write 0. Okay, so now let's just solve these 2 integrals here. We got this integral, and the electric field in the region of B and C is, if we remember here, to show it. Okay, we got electric field in that region. It's just with epsilon, so that's how we're gonna keep it, okay? I'm not gonna write the full representation like this. I'm just gonna keep it as a general notation. So I'm gonna write Q over 2 pi RL epsilon, okay? And that encompasses this formula, right? This here, which tells us things about the inside of the dielectric. Okay, so I'm just writing the general notation here. All right, and that is dotted with dr minus b to a. The electric field in the region from b to a, from a to b, is here. We have epsilon naught. So q over 2 pi rl epsilon naught. Okay, and that's between a and b here because we're in a conductor. So in a conductor, epsilon naught, because the chi is 0. We have epsilon naught for the conductor region, and that's it. Okay, so now let's evaluate the integral. So we got, let's see, we got I don't want to do it in one step, but maybe I will, maybe I won't. Okay, so I'm going to take out the q, 2 pi l, and then the epsilon. And then all I have left is the integral of 1 over r, right? So the integral of 1 over r dr is ln. And so I am going to write ln of b minus ln of c. So I already evaluated the integral. All right, so if you didn't know what I did here, let me put it over here. We got a negative b c. I took all the constants out, which is q, 2 pi, l, epsilon. Let's keep the negative outside. Sorry for this weird parentheses, but the negative is outside. And then I have 1 over r left inside. This is ln, and then evaluated at the limits, we got ln of b minus ln of c. Okay, that's how I got this part. And so we're gonna do the same over here. I'm gonna pull out the negative, q over 2 pi l epsilon naught. You see I did it again. You see this epsilon? And so just know that this epsilon is the same thing as this. That's just my notation. All right, so we got this, the integral is 1 over r, and evaluating at the limits, we got ln of a minus ln of b. Okay, so properties of ln, let's put one on top of the other. Let me see, let me close this off. Properties of ln, so we have ln of a minus ln of b. We can write that as ln of a, and then the minus 1 goes underneath. Okay, so that's what we're gonna do here. Before we do that, actually no, after we do that, I don't like to mess with the signs while I'm doing the problem, so I'm gonna write it out, fully. So we have negative q over 2 pi l epsilon, and here we have ln of b over c. Okay, and then over here we have minus q 2 pi l epsilon naught, and we have ln of a over b. Okay, so this negative with the ln, another property of ln, so we have negative ln of b over c. That's the same thing as writing ln of c over b. Okay, so let's do that. We got potential is equal to q over 2 pi l epsilon ln of c over b. Okay, and then plus q over 2 pi l epsilon naught and ln of b over a. Sorry, I changed my epsilons, but just know it's the same thing. I don't like writing these actually. These I feel comfortable with. All right, so we got that. And what other tricks do we have? Let's take out everything that's in common, right? And we're also gonna take out epsilon naught. Okay, so let's do this. We're gonna take out a q, we're gonna take out 2 pi L, and let's take out epsilon naught. Okay, this first term stays with the epsilon on the bottom, but it gains 1 on top. Okay, and we still have ln of c over b, and plus ln of b over a. So this one got rid of the epsilon naught. Over here, you gained 1 on the top, so it cancels out when you go in. Okay, so now this right here, if you remember from our representation for absolute permittivity, right, we rearranged it, and here we have this, which is, if we flip this, it's going to be 1 over epsilon r is equal to epsilon naught over epsilon. So which is what we have here. So let's change this into 1 over epsilon r. Okay, and then we write everything again. Okay, q over 2 pi L epsilon naught, potential. Okay, so that's it. This is our potential. All right, and let's put it here in pink. All right, that's our potential, our net potential. Let's just write it out here. Net electric potential. Okay, and now finally, what we started looking at in the beginning was capacitance per length, right? This notation is what we started looking at, and now we can see where we're going to put it, so, or how we're going to use it. We have capacitance over the length, right? So capacitance per unit length. Here we have potential, and we have our formula. Let me write this. I'm gonna start over here. So all of this, okay. All right, so we have one more formula that is Q is equal to CV, right? We rearrange that. We got capacitance is equal to charge over potential. And I just wrote V and phi, but just know that potential and this notation is the same thing. Nomenclatures. It's whichever one you prefer. So this and this phi are the same thing. So don't, get that confused. All right, so this is what we want, capacitance. We have Q, or we have a general Q, which is what we've been representing, and we have potential. So now you could see that finding potential was necessary, and now that we have that potential, the net potential, the whole thing, we can represent Q, the general Q for the whole thing, and our capacitance per unit length. So let's see how we can do that. Let's do something right away so we don't get confused. Let's just divide both sides by L. So this divided by L, and this side divided by L. Just perfectly legal, right? So capacitance per length is equal to Q over length times potential, the net potential. So this is really what we're looking for here. All right, so let's put all the values in that we have and see what we got. So let me leave this here. Okay. All right, so let's put all the values we have. So we got C is equal, or C over L, sorry. C over L, this is a L, by the way. Q, let's leave Q on top, right? L here, and I'm gonna write this whole thing inside of here. So we got Q over 2 pi L epsilon naught, 1 over epsilon R, and C over B. Everything else comes along. Okay, so I see things that want to cancel out. All right, we have, let's get a different color. All right, we have here L, which cancels out on the right side, and we have Q, right? If we flip this to the top, then we have Q. This is a tricky algebra move, so maybe I should do it in some steps. Okay, so let's see. Yeah, let's just do it, whatever. I want to show just this part right here on top over here. So we have Q, which is this Q, over, I have this fraction on the bottom. So we're going to take it piece by piece, right? 2 pi L epsilon naught, and we don't have the L anymore. So if I flip it up, right, I'm going to have 2 pi epsilon naught over Q. So all this goes away. The Q's cancel. All I'm left with is 2 pi epsilon naught on top. So just from this, I'm left with a 2 pi epsilon naught on the top. Now, when it comes to this right here, all right, we're gonna have to flip all of this, right? And let's see. Actually, we probably, no, we don't at all. We could just leave it like that. Okay, so this was just a problem. All right, so let's rewrite it. We got C over L, capacitance per length. The Q's canceled, right, and left us with just 2 pi epsilon naught on top. So 2 pi epsilon naught. And then all that is over, we have ln of B over A, write this one first, and then plus 1 over epsilon R, ln of C over B. And that's it. All right, so let's highlight it with this. Okay, so that's capacitance per length. So just to recap real quick, we had this wire with a conductor, a copper tube in the inner radius, and then the area from B to C is filled with some dielectric material of constant ER. So capacitance per length led us to look at, or start off with, usually, Gauss's law for electric displacement, right? Leave the Q, you know, there's no charge here represented, just leave a general Q. And this is telling you how the flux is associated with the electric displacement along each material or in the radial direction, right? And so from there, we can use this formula that relates the electric displacement and the electric field with a factor of epsilon, the susceptibility. We rearrange it for electric field, and we need to note these representations for the absolute epsilon, right? So it's epsilon naught and epsilon R, which is specific constant for a material. So, and this one's free space. So the electric field in 3 different regions, right? 0 on the inside, because right on the outside is the conductor. There's no Q here on the inside, and epsilon naught here between A and B, right, is gonna be represented with epsilon naught, which is the total epsilon over epsilon R. So we got that, and then here we have, right here between B and C, we have ER, so we're just gonna represent it as E. So this is nothing, this little dot right here, so it's just epsilon. All right, and remember that epsilon is epsilon naught 1 plus chi E. Usually we're used to writing epsilon naught, but remember that chi E in a vacuum the susceptibility is 0. So if we're not in the dielectric, then chi E is 0. So we need this electric field represented in the different regions in order to look at the polarization in the different regions also. All right, so this is the formula relating polarization to electric field by factors of the susceptibility, the dielectric constant. All right, telling us how we need to move inside the dielectric. And in the first region, which I labeled R less than A, right, in the inside, here it's 0 because electric field is 0. And so we have, where's it at? Second region, P2 is the outside, right? I jumped all the way to the outside, and chi is 0 in a vacuum. So this is a vacuum, we're not in the dielectric anymore. And so it's 0 because chi is 0. And now the interesting part, we have P3 in this region here, and we have epsilon naught, and then we solve for chi E using the formulas here, where what's representing the absolute dielectric, and we have ER minus 1, and then this region right here, B, R is between B and C. So R is between B and C. It's the region we chose, and we write Q 2 pi RL epsilon. We represent it with this notation. Things cancel out, and we have our polarization in that region. Right? Then finally, we look at the potential. So this here is potential. And looking at the net potential means that we're traveling from the furthest part of the dielectric, which is here, which is C, right, inward towards B, so C to B, and then from B to A, right, which is this one, and then from A to 0, which is all the way to the center. And so that gives us the net potential. We don't want the potential out here, all right, so we're only interested in the dielectric. These 3 integrals, right, we got a couple little tricks with some LM properties, which is fine. And when we pull out epsilon naught, we got this representation, which we should change to this. And that's it. And then finally, we got the last formula we need, which is Q, the charge, is equal to capacitance times the potential. Remember that potential could be written with V or with phi, so I switched it up here, but just know it's the same thing. And then I divided both sides by L, right? Because, you know, we could do that, that's fine. They both cancel out, so capacitance per length is equal to charge over length times potential. And then since we found the potential, the net potential, we substitute that in, things cancel out, and here we have our capacitance. Capacitance per unit length. Okay? All right, you guys, hope that helped. Thank you for watching.